Hello.
Yes, sir.
Anyone can respond. Is it audible to you?
Yes,
Yes,
sir.
sir.
Hello.
Yes, sir.
Audible, sir.
Hello.
Yes, sir.
Okay, okay, okay. Can you see the screen?
Yes, sir.
Okay, we'll start the class. So today's class is about normal incidence. Okay, so it is different from the previous topics what we have studied. Now it is a new one. Okay, so that means it is different compared to the previous topics. We have studied about the propagation of the electromagnetic wave in different media like free space, lossless dielectric, lossy dielectric, and in good conductor. We have seen the propagation of the wave and how the signal is attenuated, what is the phase shift, what are the relations between alpha and beta, what is the velocity, what is the intrinsic impedance, all those things we have seen. And then we have studied about the pointing theorem, which is giving about the power flow. Okay, actually pointing vector P bar will give power density. Then from that we can calculate the power. Okay, how much amount of power is propagated through certain area also we have calculated and we have done one problem also. Then the next topic is about the normal incidence and oblique incidence. So it is completely different from the wave propagation. Okay, we will talk about the wave propagation only, but it is about two media. Okay, we have studied boundary conditions in electrostatics and magnetostatics. Okay, so when the electric field is going from one medium to another medium, I told clearly that at that particular time the waves will be refracted. Okay, so now we are going to talk about that one. The waves will be refracted uh, based on that particular electrostatics boundary conditions and magnetostatic boundary conditions. Now what will happen, we'll see. So whether we are going to study about this normal incidence or the oblique incidence, here we have to consider two media. So for this particular topic, normal incidence is somewhat easy only. But oblique incidence is very difficult to understand. But once you understand, that is okay. But difficult to understand about the oblique incidence. So lot of attention is required here. Okay, for this particular topic. Okay, not for the normal incidence. That means you have to listen this one carefully. Same terminology we are going to use for the oblique incidence also, but understanding the oblique incidence is very difficult. So you have to listen very carefully. So first we will see the normal incidence. It is quite simple. Okay, so see carefully. What is about this particular topic is nothing but here we have to take one boundary. One boundary, you assume this is not a line, it is a surface. Okay, so in our boundary conditions topic also I have mentioned clearly that boundary is a surface, not a line. Okay, so that if you are talking about the charge, rho s will be available, surface charge density will be available, and surface current density will be available, k bar. But we did not take rho l. Okay, we did not take I. Okay, so these are the reasons. So boundary is always surface. Boundary is always surface or plane. Boundary is always surface or plane. And here we will consider x is the xy is the boundary. So that I am taking like this. X, whatever you are seeing on the screen, and y is coming out of the screen. Here I have taken dot circle. So it is coming out of the screen. So you have to visualize the xy plane. And because it is online, I cannot show with my hands also. In the if I on the camera we can show, but it will take a lot of time. So if you have any doubts, we'll see later. Okay, then you have to visualize now the boundary, that is xy plane. So x is the vertical line what you are observing, and y why completely you are not observing? Just dots are I have given. So the positive y-axis is coming out of the board. So you have to visualize that one properly. So XY plane you have to visualize, and this XY plane is dividing this particular screen or the space into two parts. One is left side of this one, and second one is right side of this one. Because XY plane is there, here we can take it is z is equal to 0. XY plane means z is equal to 0. YZ plane means x is equal to 0. All those things we know. So because it is XY plane, we can take here z is equal to 0. So left side part is z is less than 0, and right side part is z is greater than 0. Okay, so this plane, this surface or this boundary is separating this particular space into two media. One is left side of this one. We are indicating that one with z is less than 0, and right side of this one we are indicating with z is greater than 0. Okay, and we know very well about the direction of the surface. Okay, what is the direction of the surface? Means perpendicular to the surface we have to take. So surface is xy plane. So perpendicular to that one will be z axis only. So your z axis is the normal. Normal means perpendicular. So we can take like this. Okay, so now what is the normal to the boundary? Z is normal to the boundary. So first you have to understand this particular setup. Okay, what is normal incidence? Next I'm going to tell. First you understand this particular setup. We have taken the boundaries XY plane, X line you are observing, X axis you are observing on the screen, that is vertically available. Why you are not observing on the screen? Okay, why I have indicated with the dot circle. Okay, why I have indicated with the dot circle. So positive y-axis is coming out of the screen, and negative y-axis is going into the screen. So this xy plane itself is our boundary, and we have represented that one with z is equal to 0. So this boundary is like a paper. It is plane, okay, which is separating the space into two media. One is left side of this one, second one is right side of this one. So z is less than 0 is medium 1, z is greater than 0 is medium 2. Okay, this is a setup. Next, the perpendicular or the normal to the interface is z, because xy plane we have taken. So what is the perpendicular to the xy plane means the z axis. Okay, so z is the normal thing here. Normal I'm indicating with the n cap. Okay, then how to characterize the two media available here? Okay, when can we say the right side part of the boundary is different from the left side part of the boundary? Means, or when can we say this medium 2 is different from medium 1? Means we have to see the characteristics of the medium. What are the characteristics? Means conductivity. Okay, then we can tell permeability, then we can tell permittivity. So because it is medium 1, I'm representing with the sigma 1, mu 1, and epsilon 1. Similarly, in medium 2, the conductivity we are representing with sigma 2, and permeability is with mu 2, and permittivity is with epsilon 2. So in this manner, we have taken the two media characteristics. So because sigma 1 is different from sigma 2, or mu 1 is different from mu 2, and epsilon 1 is different from epsilon 2, we can tell their impedances are also different. Because what is the equation for the eta? Eta is equal to j omega mu by sigma plus j omega epsilon. We have studied already j omega epsilon. J omega epsilon. As we are working with medium 1, this mu 1, sigma 1, and epsilon 1 I am taking. Okay. Similarly, you can write equation for this eta 2 also, that is j omega mu 2 by sigma 2 plus j omega epsilon 2. As sigma, mu, and epsilon values are different for the two media, you will be getting two different values for eta 1 and eta 2. That means impedances are also equal. Sorry, impedances are also different in medium 1 and medium 2. This is the major point. Okay, this is what we need to remember. Okay, so how can I tell these two media are different? Means simply you can tell that the impedances are different. Okay, the impedances are different. Why? How can we tell if the impedances are different, the two media are different? Means you see the equation. The equation is involving permeability, permittivity, and conductivity. If any one of these, at least any one of these three parameters is different, then we can tell those two impedances will be different. That's why those two media are also different. So like this, we can able to consider. Okay. So now whatever I have told you, this is just a setup only. You need to understand this one carefully. Okay. So then now we will see what is normal incidence. So here, actually the topic is about when we incident one electromagnetic wave from medium one onto the boundary. That means actually we want to send this particular electromagnetic wave from medium one to medium two. So when we send the electromagnetic wave from medium one to medium two, it is incident on the boundary, that is XY plane here. Okay, so it will go like this. After incidenting on this particular boundary, certain part of the incident wave will be transmitted into the medium 2, and because of the impedance mismatching, that is eta 1 is not equal to eta 2, so certain part of the input signal will be reflected back. This is what is going on actually. Okay, because eta 1 is different from eta 2, the complete incident wave, this is the incident wave, the complete incident wave cannot able to travel into the medium 2. Only certain portion of the incident wave will be transmitted into the medium 2, remaining will be reflected into the medium 1. So we have initially we have only one wave in our hand, but now we can see three different waves. One is incident wave, second one is transmitted wave, and the third one is the reflected wave. Okay, just you observe this particular criteria: incident wave, transmitted wave, and reflected wave. Okay, and now orally, if you see in medium one, now how many waves you are observing, and in medium two, how many waves you are observing? In medium one, we are observing two waves. One is the incident wave, second one is reflected wave. In medium two, we are observing only one wave, that is the transmitted wave. Okay, so we have incident one particular electromagnetic wave. Out of this electromagnetic wave, certain amount of power will be transmitted into the medium two, and the remaining power is reflected back into the medium one only. Okay, what is the reason for this one? Means impedance mismatching. That is eta one is not equal to eta two. If both the impedances are equal, what is the meaning of that one? That is the same medium. Okay, so same medium is nothing but it will be propagating continuously. That is what you need to understand. Okay, now certain assumptions we'll take here. Now we have to take a incident electromagnetic wave, transmitted electromagnetic wave, and a reflected electromagnetic wave carefully. Okay, so I'm telling that for the incident wave, the electric field is oriented in X direction, the magnetic field is oriented in the Y direction, and direction of propagation is along Z direction. That already we know. Okay, wave we are sending from medium 1 to medium 2. That means wave is propagating in the Z direction only. Okay, so direction of propagation is Z. This is our assumption only. There is no rule that you have to take electric field orientation is in the X direction only. There is no rule like that. Okay, so then for the transmitted wave, how these orientations will be available? Electric field is still in X direction only. Magnetic field is still oriented in the Y direction. And after entering into medium 2, the wave is propagating along the Z direction. Same thing. Okay. Now for the reflected wave. Now listen carefully. For the reflected wave, the electric field still I am taking in the X direction only, but magnetic field will be in opposite direction, that is minus Y direction. Okay, and direction of propagation is, can you tell, can anybody tell what is the direction of propagation for the reflected wave?
Opposite.
Minus it.
Huh? What is the direction of propagation for the reflected wave?
Opposite to transmitted wave.
That means in which direction?
Minus Z.
Minus Z. Okay, so like this we have to take. So because the direction of propagation is in the minus Z direction, this has to be reversed. Okay, these are the two important points we have to understand here. This one and this one. Now, whatever I have written here on the slide, this information we have to keep in the form of the diagram. Okay, so in the next slide, I'm going to show that one. This diagram is very, very important. Okay, this is the boundary actually. The boundary we have taken XY plane. So Y is coming outside, positive Y is coming outside, negative Y is going inside. Okay, now, as I said earlier, I'm concentrating on the incident wave first. So in the incident wave, the electric field is oriented along the X direction. So EI, this is suffix I is indicating that it is related to incident wave, and the direction of propagation is along the Z direction. Okay, and now already I have given the information that the magnetic field of the incident wave is available in the positive y direction. Positive y direction means coming out of the screen. That's why I'm representing with a dot circle. Okay, this is the information about the incident wave only. Is it okay? Anyone is having any doubt regarding this particular representation? It is about incident wave. In the incident wave, already I have given that wave is propagating along the z direction. Okay, that is what I have represented here. Then electric field, magnetic field, and the direction of propagation. These three must be orthogonal to each other directions. So electric field is oriented in the x direction. Magnetic field is oriented in the y direction, that is coming out of the screen, and the direction of propagation is along the z direction. So we have satisfied those conditions. Okay, orthogonality condition. Is it okay? Anyone can respond. Is it okay?
Yes, sir.
Okay, then we will talk about, we will draw the related things regarding the transmitted wave. Okay, so transmitted wave is also propagating in the positive z direction only, and the transmitted wave electric field is also oriented in the x direction only, and magnetic field of the transmitted wave is also oriented in the y direction only. So there are no changes here, but it is transmitted wave. That's why I need to represent with the ET. Okay, suffix T represents the electric field of the transmitted wave. Similarly, HT. Okay, this is the magnetic field magnetic field of the transmitted wave, and it is propagating in the Z direction. These two are similar. Okay, throughout our topic, not only in the normal incidence, in the oblique incidence also, these two will be in the same manner. Okay, incident wave directions and transmitted wave directions, you can able to work these two similarly. But when you go for the reflected wave, now listen carefully. Already I have given the directions for the electric field, magnetic field, and the direction of propagation in the previous slide. Accordingly, we are going to draw the diagram here. Okay, so whether it is a reflected wave also, I have taken the direction of the electric field in the incident wave direction only. That is nothing but in the positive x direction. And because of the impedance mismatch, the reflected wave is going in the negative z direction. So direction of propagation is in the negative z direction. That is what I have indicated. Now the magnetic field of the reflected wave is, now we are representing with the cross circle. What is the reason for that one? It is available in the negative y direction. So this is what you have to understand very carefully here. Okay, so I will tell once again, there is no change in the direction of the electric field. So it is oriented in the positive x direction. But the direction of propagation of the reflected wave is in the reverse manner. That means it is going in the negative z direction. So we have understood about electric field and we have understood about the direction of propagation. In order to satisfy these two, the magnetic field must be oriented in the negative y direction only. Okay, if you have any doubts here, you can use your uh, right hand thumb rules. Okay, so now listen carefully. Okay, because it is the online class, you cannot able to see my fingers, how I'm orienting this electric field, magnetic field, and direction of propagation. Okay, so carefully you listen. Throughout our topic, we are using our thumb, right hand thumb, for the direction of propagation. Okay, right hand thumb for the direction of propagation. Slowly you try to understand. thumb we are using for direction of propagation of the wave. Okay. And forefinger we are using for electric field. And the middle finger we are using for magnetic field. So throughout our topic, this is the criteria we are going to use. Okay. Now you apply this one for incident wave only. Apply this one for the incident wave only. Okay. Carefully observe. Okay. So you need to keep your right hand forefinger in the direction of the electric field. Then your middle finger should show that it is coming out of the screen. I'm telling about the incident wave. Then your thumb automatically represents the direction of propagation. You have to try this one. Okay, incident wave is in the x direction, incident electric field. That means your forefinger is in the x direction and the middle finger is indicating y direction and thumb is indicating the z direction. Did you observe this one for the incident wave? Hello, have you observed this one?
Yes, sir.
Okay, same thing is there for the transmitted wave also. Okay, you take your right hand thumb rule, right hand these three fingers. This forefinger is for electric field and middle finger is for the magnetic field that is coming out of the screen. Okay, then this thumb is indicating the direction of propagation. Now you are indicating the transmitted wave. Now exactly what we need to do means just I want to represent, see, listen carefully. Just I want to represent for the reflected wave. That means the direction should be changed. So whatever the our right hand thumb is indicating towards right side now. Now simply you rotate your hand in such a way that you rotate your hand in such a way that thumb should represent a negative z direction and forefinger should represent upside only. Okay, your forefinger should represent the positive x direction only. Thumb should represent a negative z direction. So now you observe your middle finger. It is indicating inside into the screen. Is it correct?
Yes, sir.
Your forefinger is in the x direction. Your thumb is in the negative z direction. So automatically you should represent your middle finger is representing the negative y direction only. That means going into the screen. Have you observed this one?
Yes, sir.
Okay, did all of you understand this one?
Yes, sir.
You should not by head or you should not try to remember this particular diagram. You don't try to remember this particular diagram. According to the concept, automatically it should be drawn. Okay, if you have any doubt, any one of you, you please ask me. I will explain once again. Otherwise, I will switch on the camera and I will show my hand because it is very essential to understand the oblique incidence also. Okay, I have to stop sharing also. Is it okay now?
Yes, sir.
So can you see me?
Yes, sir.
Okay. So it is very difficult for me. Okay, we are using like this. Okay, three fingers. So for the it may also be difficult for you to understand. I don't know how to show. Okay, with respect to the diagram, what is there on the screen? I am representing like this. Now thumb is indicating right side. It may be reverse for you, know. How can you see this one? Thumb is in the right side, forefinger is in the upside, and middle finger is coming out of the screen. Is it okay? This is about the incident wave or for the transmitted wave. But when I try to represent this uh, reflected wave, what I need to do, whatever the thumb is indicating the direction of propagation in the positive z direction, I have to reverse like this. Then my thumb is indicating now in the negative z direction. Okay, but I did not change the direction of the forefinger. That means we did not change the direction of the electric field. Okay, so this is the first case. That means it is for both incident wave and transmitted wave. When you try to change the direction of the propagation instead of positive z direction, if you want to represent in the negative z direction, I have changed you like this. So in this particular rotation, if you observe carefully, thumb direction is changed, middle finger direction is changed, but there is no change in the direction of the forefinger. It is representing the upwards only in both what we can tell incident wave and the reflected wave. That means electric field direction is not affected. Okay, magnetic field direction is affected and the direction of propagation is affected. Okay, so this is one that I want to show. Is it okay? Still anyone is having doubt? 1 second, I will tell. Okay, can I continue? Hello.
Yes, sir.
Okay. Okay, next. So in this way, we have to draw the diagram carefully. Then equations. Okay. So boundary conditions we know, and we are assuming that here there is no surface charge density. Okay. And there is no surface current density. So that the tangential components will be equal. That means HT1 is equal to HT2 and ET1 is equal to ET2. Okay, that means total electric fields available in medium one, tangential components of the electric fields available in the medium one should be equal to tangential components of the electric fields in medium two. Similarly, this magnetic fields also. Okay, so these two things we have to apply. Okay, then related equations we are going to get. But here what is happening in medium one, we are observing here two waves are there. One is incident wave. Second one is reflected wave. But in medium 2, we have only one wave, that is transmitted wave. So there is no problem here. Okay. So first of all, I want to apply this particular boundary condition, that is ET1 is equal to ET2. This one refers to medium 1, but in medium 1 we have okay, you may confuse with this this ET, this ET. So I will take E tan 1, tangential component of electric field in medium 1, tangential component of electric field in medium 2. So this is involving two signals. One is incident wave and second one is reflected wave. This is involving only one signal, that is a transmitted wave. Okay. Now, what is meant by tangential components means you see carefully now the diagram. Diagram is important in order to write the equations for this particular topic. So what is our boundary? XY plane is the boundary. That means perpendicular to the screen. X is a vertical line and this Y is coming out of the screen. You have to visualize that one. Okay. So our electric field EI, okay, that is exactly available parallel to the boundary. EI is parallel to the boundary. Okay, Z is normal to the boundary, but EI is parallel to the boundary. Similarly, if you come to this uh, reflected wave, ER is also parallel to boundary because ER direction is towards X direction only. EI direction is also towards X direction only. ET direction is also towards X direction only. Boundary is XY plane. So EI, ER, ET all are parallel to the boundary. That means all these are directly tangential components only. But in medium one, we have both incident wave and reflected wave. So total tangential component in medium one is given by addition of these two. But in medium two, we have only one electric field tangential component, that is ET only. So this is one equation. By the application of this boundary condition, we got this is the equation. Now we'll apply second one. That is HT1 is equal to HT2. Okay. So again, same rule. Here I'm taking tan, here also tan, tangential component in medium one. So again, in medium one, we have incident wave, reflected wave. So incident wave magnetic field is there, reflected wave magnetic field is there in medium one. Okay, and in medium 2 only transmitted wave magnetic field is there. So accordingly we have to write. Now see carefully here. One twist you will observe for the incident wave. What is the direction of the this magnetic field? It is in the positive y direction. Okay, so this is what you have to observe. Dot circle for the incident wave. I am telling. So for the incident wave, the direction of propagation. Sorry, the orientation of the magnetic field is along the positive y direction. Boundary is a XY plane. That means it is a vertical line coming out of the screen. So it is again parallel to our boundary. So HI is directly parallel to the boundary. Similarly, HR is going into the screen, but it is perpendicularly going into the screen. So it is also parallel to the boundary. HI is parallel to the boundary, HR is also parallel to the boundary, and HT is also parallel to the boundary. It is coming out of the screen, and XY plane is infinitely long enough so that HT is also parallel to the boundary. So HT is also tangential component, HI is also tangential component, HR is also tangential component. But HR direction is negative y direction. HA direction is positive y direction. Because of this reason, when you try to write HT1, we have to take HI minus HR. This minus we have to take. This is the key point here, and it is equal to only one component is there in medium 2, that is HT. So this is the second equation we got because of the application of the second boundary condition. So this minus you should not forget. Okay, why we have taken minus here? The reflected wave direction for the direction of the magnetic field component of the reflected wave is in the negative y direction, whereas the direction of the magnetic field of the incident wave is in the positive y direction. So both are opposite to each other. So that we have taken minus symbol here in order to illustrate that one. Whereas in case of the electric fields, both electric field of the reflected wave and electric field of the incident wave both are representing in the towards positive x direction only. So that the summation is enough here. But here we have to take like this. Okay. So I'm going to the next slide and I will write these two equations once again. So first equation we got EI plus ER is equal to ET, and the second one we got HI minus HR is equal to HT. This is equation 1. This is equation 2. Okay. Now, what we need to do means we will write this magnetic fields in terms of the electric fields only. And we have the relation with respect to impedance. Okay. So we have the relation with respect to impedance. E by H is equal to eta. So H is equal to what we can write? E by H is equal to we can write E by eta. So here I'm replacing this HI with EI by incident wave is related to medium 1, that means eta 1 minus. This is ER by HR is nothing but ER by. This is also related to in medium 1 only, that's why eta 1. It is equal to HT is equal to ET by eta. But transmitted wave is related to medium 2, that's why eta 2. Okay, but you may understand where did I write eta 1, where did I write eta 2. Now it is E3. So now equation 1 and equation 3 we have to solve. Okay, for what purpose we have to solve means now one concept I have to tell, that is the reflection coefficient. Reflection coefficient. Second one is transmission coefficient. So as I said earlier, here when this is a boundary, when you transmit one wave, because of the impedance mismatch, only certain portion will be going into the medium 2, remaining will be reflected back. How much portion is reflected back, how much portion is transmitted into the medium 2 with respect to this incident wave, we have to talk. Okay, it is reflected, it is transmitted. Okay, so this is wave. This arrow is representing the wave. Okay, not electric field. Reflected wave. This is the incident wave. It is a transmitted wave. Okay, so what I need to get means how much amount of reflected electric field is there with respect to incident electric field. This is what we need to tell. Okay, and how much amount of transmitted electric field is there with respect to incident electric field. This is what I need to calculate. So we are telling the amount of the reflected electric field with respect to incident electric field, and we are telling the amount of transmitted electric field with respect to this incident electric field. So the measure of this one is said to be reflection coefficient, because it is about the reflected electric field. It is about the reflected electromagnetic wave. So that it is called a reflection coefficient. Reflection coefficient is indicated with the gamma. Okay, so gamma is equal to, we can write reflected electric field by incident electric field. And the transmission coefficient is represented with the tau. It is about how much amount of transmitted electric field is there with respect to incident electric field. Okay, so these are the definitions of the reflection coefficient and transmission coefficient. Now we have to get this reflection coefficient and transmission coefficient in terms of impedances we have to get. Okay, what we will get in the sense eta 2 minus eta 1 by eta 2 plus eta 1, and the transmission coefficient we will get 2 times of eta 2 by eta 2 plus eta 1. So in terms of the impedances, we are going to get this reflection coefficient and a transmission coefficient. So this is our job. We are going to do this particular job now. Okay. So we have two equations. So by solving them, we can able to get these ratios. We have to solve for these ratios, ER by EI and ET by EI. So I'm going to solve them in the next slide. So EI plus ER is equal to ET. EI by eta 1 minus ER by eta 1 is equal to ET by eta 2. These are the two equations we have. Now, for example, I need to get gamma. Okay, what is the equation for gamma? Gamma is equal to reflection coefficient, that is ER by EI. That means I don't want ET. Okay, so you replace ET in this equation. Okay, using the first equation. You take it is a, already we have taken 1 and 3. So substitute 1 in 3. Okay, in place of ET. So what you will get? So EI by eta 1 minus ER by eta 1 is equal to ET means EI plus ER by eta 2. And to get EI by ER by EI. So write all the ER terms at one place, write all the EA terms at one place. So I'm writing EI. Here also we have EI. So if you take left side, we are going to get 1 by eta 1 minus 1 by eta 2. And by writing ER terms at one place, at right side already we have ER by eta 2, that is 1 by eta 2, and left side we have minus ER by eta 1. By bringing that one to the right side, here we will get 1 by eta 1. Okay, so take LCM on both sides. Here we will get eta 2 minus eta 1 by eta 1 eta 2, and it is equal to this side ER times, here also we can write eta 2 plus eta 1 by eta 2 eta 1. So on both sides we can cancel eta 1 eta 2, and I can write equation for ER by EI, that is equal to gamma, that is equal to what we can tell, eta 2 minus eta 1 by eta 2 plus eta 1. Very, very important equation. Okay, this concept, whatever the reflection coefficient concept is there, this one you are going to see in our transmission lines concept also. Okay, last topic of the module 5 is the transmission lines. After completion of this electromagnetic waves, some topic is there regarding the transmission lines. There also the similar content will be there. Okay, so anyhow we will talk about that one later. Here the reflection coefficient, now we got eta 2 minus eta 1 by eta 2 plus eta 1. What is eta 1? Impedance of the medium 1. Eta 2 is the impedance of the medium 2. Okay, this is about gamma. Now we need to get equation for, now we need to get equation for transmission coefficient tau. Tau is equal to, I said, Et by Ei. Okay, so in media, in what we can tell, we need ET and EI. That means we have to replace ER. So take 1 in 3, but replace for ER. Okay, because we don't want ER now. So I can write like this, EI by eta 1 minus, in place of ER, what we can write, ET minus EI from the equation 1. So ET minus EI by eta 1. It is equal to ET by eta 2. So write all the EA terms at one place. EA, if you write EA by eta 1, here also minus into minus is place EA by eta 1. That means 2 times we are writing. So 2 by eta 1, it is equal to, by writing all the ET terms at one place, 1 by eta 2. This side minus ET by eta 1 is there. By bringing to the right side, it will become place. Like this will get. And it is equal to, by taking LCM, you will get eta 2 plus eta 1 by eta 1, eta 2 into ET. Okay, so you observe this one and this one, we can cancel eta 1, eta 1. So now you can write comfortably the equation for ET by EI. So it is equal to, what will you get? 2 times of this eta 2 will go to the numerator, 2 times of eta 2 by eta 2 plus eta 1. This itself is our tau. Okay, so this is also equivalently important equation. Okay, so we got 2 equations now. I'm going to write in the next slide. Reflection coefficient gamma is equal to eta 2 minus eta 1 by eta 2 plus eta 1. And tau is equal to, we got 2 times of eta 2 by eta 2 plus eta 1. Okay, so this is indicating ER by EI, and this is indicating ET by EI. And we are telling this is a you see the incident we have taken normal to the boundary. Which direction normal to the boundary is there? In the Z direction. So wave is also propagating in the direction. Okay, this incident wave is propagated in the Z direction only. Z direction is what? It is normal to the boundary. Boundary is XY plane. Okay, boundary is XY plane or Z is equal to 0 plane. Normal to boundary is Z direction. So the incident wave, we can tell incident wave was incident normal to boundary. So how we have incident, the incident wave onto the boundary means normally. That's why this incident is called normal incidence. You incident in any manner, if there is a impedance mismatch, surely we can tell there is a reflection. Okay. Impedance of the medium 1 is eta 1, impedance of the medium 2 is eta 2. So because of the impedance mismatch, eta 2 is not equal to eta 1. So only some part will be transmitted, remaining part is reflected. This is what we have observed. Okay. Now special case will take. Special case is medium 2 is a perfect conductor. Medium 2 is a perfect conductor. Perfect conductor means sigma is infinity. Then what is the eta 2 value? Eta 2 is equal to, what is the formula? J omega mu 2 by sigma 2 plus j omega epsilon 2. As sigma is infinity, you will get eta 2 is equal to 0. Otherwise, simply you can think for the conductor, impedance is 0. Okay, resistance is 0. So eta 2 is 0. Now you calculate gamma and tau. Okay, special case is, instead of taking the dielectric medium, okay, on the both sides, two different dielectric mediums, I'm taking medium 1 is dielectric only, but medium 2 is the perfect conductor. So perfect conductor is having eta 2 is equal to 0. Now you substitute in the formulas, gamma is equal to eta 2 is 0 means 0 minus eta 1 by 0 plus eta 1. That means minus 1 we are getting. And tau is equal to eta 2 is 0 means numerator itself is 0. So this one will get. So what is the meaning of this one? It is not about just getting the values for the gamma and tau. From that we have to get the conclusions. So in the next slide I'm writing, okay, eta 2 is 0 for the perfect conductor. That means medium 2 is a perfect electric conductor, like this we can take. So in this particular case, we got gamma is equal to minus 1 and tau is equal to 0. So what is the meaning of this one means? See, if your second medium is conductor, perfect conductor, you have incident one electromagnetic wave. Then what is happening? You see here eta 2 is equal to 0, eta 1, some eta 1 is there. You got here reflection coefficient is 1, minus 1. So what is the meaning of that one? ER by EA. And here transmission coefficient is 0. That means ET by EI. So just to cross multiply these two equations, you will minus EI and ET is equal to 0. So there is no transmitted wave. When you take medium 2 is a perfect conductor, you got here transmitted electric field is 0. That means that transmitted, there is no transmitted EM wave in medium 2. That is what we can tell. So in our basics also I have told that there is no electric field in the conductor. That is what we have observed here also. Okay, so when this is a situation, if you take the medium 2 is a perfect conductor, this electromagnetic wave cannot penetrate into this particular perfect conductor. So everything will be reflected back only. That means what is transmitted, everything is reflected back. That means in magnitude, EI is equal to ER. But in opposite direction, that is what we got here. Okay, you have transmitted here 5 watts of power, but here you have the conductor, so that total 5 watts will be reflected back, but in opposite direction. That is what you have to understand from this particular topic. Okay, so this is the way of understanding these two. And some more information I will give regarding the relation of gamma and tau. So in the next slide, again, I'm taking what is the equation for gamma in terms of the impedances means we got eta 2 minus eta 1 by eta 2 plus eta 1. And equation for tau is equal to 2 times of eta 2 by eta 2 plus eta 1. So what is the concept here? You are incidenting the electromagnetic wave on the boundary. Normally you have incident. So eta 1, eta 2, two different impedances are there. Here now you take one dielectric medium here. Okay, both are dielectric mediums only. Okay, that perfect conductor is a special case. I am taking both are dielectric medium. That means some loss will be there, but electromagnetic wave is propagating. So due to the impedance mismatch, certain portion of the incident wave is transmitted into the medium 2, the remaining is reflected back. Okay, so now listen carefully. We have incident the electromagnetic wave on the boundary. So this is a total signal actually, total incident wave. Out of this incident wave only, something is transmitted, remaining is reflected. Okay, so keep this point in your mind. Now you see gamma equation and tau equation. Now you try to get 1 plus gamma. Okay, 1 plus gamma. What will you get? 1 plus eta 2 minus eta 1 by eta 2 plus eta 1. LCM is eta 2 plus eta 1. In the numerator, you will get eta 2 plus eta 1 plus eta 2 minus eta 1. So eta 1 will be cancelled. You get 2 times of eta 2 by eta 2 plus eta 1. This is exactly equal to tau. So 1 plus gamma is equal to tau we got. This is the relation between gamma and tau. Okay. So next thing is here one important question I will ask. I said that incident wave is incident wave is incident on the boundary due to the impedance mismatch. We can tell certain portion is transmitted, certain portion is reflected. That means by observing this particular statement, you can tell that now you need to answer to me. Okay, you need to respond now. Can I tell transmitted wave is lesser than the incident wave in strength wise? Hello,
Yes, sir.
anyone?
Yes,
Yes,
sir.
because incident only dividing into these two parts. Are you understanding like that?
Yes, sir.
Okay. Then with this particular analysis, we can tell that transmitted wave should be lesser than the incident wave. Is it okay?
Yes, sir.
Then you observe this equation. What did we get here? Total is 1. 1 plus something is equal to transmitted wave is nothing but transmitted wave is larger than 1 we got. Okay. Here actually denominator EI is there. So what is this equation is indicating? If something this 1 is added to reflection, then only you are getting tau. That means transmission coefficient. So it is indicating in a wrong approach actually. Total is, for example, 1. Why I'm taking total is 1 means as we have divided with the EI, this maximum content will become 1 only. Okay. So that total is 1. So total is 1. For that 1, this 1 is to be divided actually into gamma and tau. Okay. Total is divided into reflection and transmission. But here this equation is giving the wrong inferences for us. If you carefully observe, total is there. For that total, if you add gamma, then you are getting tau. That means tau is larger than the incident. Okay, transmitted coefficient, transmitted wave is showing the information from this particular equation that it is larger than the incident, but it is not true practically. Are you getting what I'm telling? So practically it is not true. So this equation is correct only. Mathematically, we have derived this equation. Then how to understand that particular criteria? 1 plus gamma is equal to tau is correct, but transmitted wave should be smaller in strength wise with respect to this incident wave. So how to understand these two opposite sides of this particular equation? Okay, that you have to answer. Okay, later. Okay, when we come to the offline classes, you need to answer that one. Okay, that is the thing. So what is the time now? Okay, it's nearly 12 o'clock. Any doubt from the starting onwards, sir? I will keep all the slides, sir. You see all the slides one by one, all the lines, sir. If you have any doubt, you can ask me. Okay. So very important concept. This is easy. Okay. Once again, I'm repeating. Whatever we have seen in this particular class, it is easy compared to what we are going to see in our next classes. Okay. So you don't keep any doubt in your mind. So if you have any doubt regarding the directions or equations, you ask me now. Okay. So normal incidence, why it is normal incidence means the incident wave is normally incident on the perpendicular incident on the uh, interface or boundary. Okay. That means it is in the direction of the normal to the interface, that is the Z direction. And something will be reflected back. For the reflection, what is the major reason means the impedances are mismatched. And how to make impedances mismatching is nothing but you need to take different values of conductivities or permeabilities or permittivities. Okay, and boundary is the plane, incident wave direction. That means incident wave means we have to talk about the direction of propagation, electric field, magnetic field. Transmitted wave also electric field, magnetic field, direction of propagation. So all these things we have to uh, take into the consideration, and reflected wave also. And many very important point is reflected wave electric field we have taken in the direction of the x only, but when we change the direction of propagation in the negative z direction, the direction of magnetic field is changed into the negative y direction. Accordingly, we have drawn this particular diagram. Then we have taken the boundary conditions. As we don't have any current density, surface charge density, we can take ET1 is equal to ET2 and HT1 is equal to HT2. And accordingly, we have provided here equations. But when you write tangential component in medium 1, itself we have the two electromagnetic waves. That's why the tangential component will be including the two terms. And in medium 2, we have only one transmitted wave. So only one component will be there in the right side part. So that we got 1 and 2 equations like that. And we replaced this H terms in terms of the E terms only. Okay, using the impedance formula so that everything is in electric fields only. And then we have defined reflection coefficient and transmission coefficient. Then by solving the equations, we got reflection coefficient ER by EA is equal to eta 2 minus eta 1 by eta 2 plus eta 1. And the transmission coefficient tau is equal to 2 times of eta 2 by eta 2 plus eta 1. And a relation we can get 1 plus gamma is equal to tau. And I asked one question regarding that one. Then by taking the medium 2 is equal to perfect conductor, we got gamma is equal to -1 and tau is equal to 0. That means completely reflected. Okay, total reflection has been done here. Okay, no transmission into the medium 2. That is what we have observed. Okay, any doubt?
So you told something in the ending about the transmitted wave showing itself as being greater than the incident wave in strength. Could you explain that more?
That you need to tell. I did not answer that one. I asked a question only. You need to answer that one when we come to the offline classes. Okay, you think about that. Search in the
Okay, sir.
books. Okay. In the rest of the topic, do you have any doubt?
No, sir.
Okay. Remaining, is everything okay for all the people?
Sir, one question.
Tell me.
Sir, does the EMF always hit the boundary incident at right angle only, or can it hit at any other angle?
No, no, no. It is only special case on a normal incidence. Next, we are going to see the oblique incidence. In that particular oblique incidence, the electromagnetic wave will be incident obliquely. That means by making certain angle to the boundary. So this is the boundary x, y. This is the normal to the boundary. Now, what we have seen is electromagnetic wave is propagating in the normal direction only. That's why that is called normal incidence. Okay, normal in which direction it is there for the boundary z direction. So electromagnetic wave is incident in the z direction only. So that it is normal incidence. Next, it is only one case. So many cases will be there. If it is a situation, boundary is xy plane, normal is z. But that normal I'm extending this side also. You may have this like this also. The incident wave can be incident on the boundary like this also. This is the incident wave. Okay, that means uh, can you tell how much angle is made by the incident wave with the normal here in the normal incidence case?
90.
What is, carefully you listen, the direction of propagation is making certain angle with the direction of the normal. Both are parallel. That means incident angle is equal to 0 in the normal incidence. But in case of oblique incidence, you see direction of propagation is like this. Direction of propagation is like this. But normal is like this. Normal to the boundary is like this in the z direction. So the direction of propagation is making non-zero angle with the normal to the boundary. That is theta I. The theta I is not equal to 0. So this is called oblique incidence. This is our next topic. But before going to see, we have to change the equation of the electromagnetic wave. It will take 1 hour. Okay. So I think in the second class from now, we are going to see the oblique incidence. Okay. Did you understand here? The normal to the boundary is Z, but electromagnetic wave is incidenting like this. Okay. Electromagnetic wave is incidenting like this. So this direction of propagation of the electromagnetic wave is making theta I angle with the normal to the boundary, that is theta I. So it has a incident on the boundary. So again, same rule, something will be transmitted and something will be reflected. Now you can see the refraction of the electromagnetic wave when it is entering into medium 2. It is not traveling like this in the same direction. Okay, whenever it is entering into, this is wrong one. This is correct one. Whenever it is entering into medium 2, the angle made by this particular electromagnetic wave with normal is changed. That is theta t. Theta t is different from theta I. Okay. So this is what we have observed. Reflection is possible. We have seen in our boundary conditions. Okay, tan theta 1 by tan theta 2 is equal, like that we have studied. So refraction is possible due to the difference in the permeativities, permeabilities, and impedances, conductivities, like that. So this is about oblique incidence. This reflected wave is making certain angle with the boundary, that is theta r. Okay, so three waves: incident wave, reflected wave, transmitted wave. Three are making certain angles with the normal to the boundary, theta I, theta r, and theta t. The relation among these three angles given by Snell's law. Snell's law is giving that theta r is equal to theta I. Always it is true. N1 sin theta I is equal to N2 sin theta 2. Sorry, sin theta t. This is Snell's law 2. This is the relation between theta I and theta t. And this is the relation. First one is theta r and theta I. It is not eta 1. It is N1, refractive index. It is not impedance. This is N2, refractive index of the medium 2. It is not impedance. Okay. We are going to see these things in the upcoming classes. Okay. So anyhow, I'm closing the session. It's already 12:05. Okay. Is it okay?
Yes, sir.
Okay, I'm closing.